All right, so yesterday we have seen a sketch of an outline of the proof of this theorem, which was saying that we give ourselves any homomorphism of the circle, and we can find, the theorem says that we can find a unique extension to the interior, which is minimal Lagrangian. Proof used anti-de Sitter geometry. And today, the goal is to sort of study how good this extension is. So in this last lecture, I will talk about the, let's say, optimality in a suitable sense of this extension, which I will define. So I'll need to talk, so this will be in the setting of Teichmüller theory, of quasi-conformal Teichmüller theory. So I'll need to introduce some notions. So the first notion is quasi-conformality. So we give ourselves a diffeomorphism from a subset of C, let's say diffeom onto its image. In C, okay, diffeom onto its image. It's not very important, might be just a local diffeom, but this is the setting we will consider. Orientation preserving. And I introduce the what is called the dilatation. So this is going to be a function, a dilatation. This is going to be a function on omega. It's a real number, which is defined in the following way. So given a point Z, let me draw a picture first. So our domain omega, it goes somewhere. We look at the differential of this function at a given point. So here we have Z. Consider a tangent space at Z of C. Because tangent space is just psychological. Of course, it's just a subset of C, but we really think about tangent spaces. So the differential of the map. Okay, and we look at the image of a circle in the tangent space. So take a circle here of any radius, doesn't matter. Its image will be sort of an ellipse, will be an ellipse somewhere. Okay, and what we look at is the ratio between the longer and the shorter axes. So f of z is the ratio between the measure axis of the differential of f at z applied to S1 over the minor axis. Actually, this, of course, doesn't depend on the radius of the circle that we have chosen. Yeah, and we say that a map quasi-conformal, F is quasi-conformal if the supremum of this function is finite. Omega of f of z is finite. Actually, we say that it is, let's say, k quasi-conformal if this supremum is equal to k. Okay. Actually, this notion can be defined for maps of much less regularity than the diffeomorphisms, but I don't want to enter into the details. But it can be defined on maps that are just differentiable almost everywhere, and I mean, much more general than that. But we will only consider diffeomorphism smooth maps, so just give the definition in this setting. And a rather easy fact is that f is one quasi-conformal if and only if f is conformal. Or otherwise it's holomorphic. So this is an easy exercise based on the fact that differential of the holomorphic map is the composition of rotations and dilatations. If you, in the more general setting of non-smooth maps, this fact is less trivial than that, but still holds. But in the smooth category, it's an easy exercise. Okay. Second notion I need to introduce is quasi-symmetry. So this is for circle homomorphisms now. So it's just for the boundary data. So now we take small f from RP1 to RP1. And we want to sort of measure how much it distorts the cross ratios. So remember that the cross ratio, so given a quadruple of points, A, B, C, D, the cross ratio of Q, and now I need to take my notes to check which definition of cross ratio I have decided to use. So otherwise, there might be a slightly difference in what I will write after. Okay. So let me make a comment on a cross ratio. Of course, basically is the only invariant for quadruple of points on RP1. So if two quadruples have the same cross ratio, then two or empty quadruples have the same cross ratio, then you can find maybe a transformation sending one to the other. But I want to give an interpretation. So we say that Q is symmetric if and only if its cross ratio is -1. This is equivalent to saying that the geodesics, so here's a picture, A, B, C, D. So cross ratio equal to -1 is equivalent to having this intersection orthogonal. So AC intersects BD orthogonally. Okay, this is a symmetric quadruple. Of course, here these geodesics. These are the hyperbolic geodesics. And in general, so this you can easily check. For instance, you just do the computation in the upper half space model for say, infinity -1, 0, 1, and gives -1. This is easily checked. In general, the cross ratio of Q is, I did the computation, is minus the tangent of the angle. So we have now geodesics that intersect with a certain angle, A, B, C, D. Did the computation yesterday night. I can't really guarantee, but cross ratio should be this formula. So basically, it goes to 0 or infinity when the angle diverges. So we define the cross ratio norm. This is the cross ratio norm of F. Is the following quantity. We take the supremum over all symmetric quadruples. Basically, we take the cross ratio. So we take any symmetric quadruple. We look at the image and look at the cross ratio of the image. And then we want to take absolute value because we want this to be positive. Then with my choice, cross ratio of a symmetric quadruple is -1. Then we take log, and then we take an absolute value again. So for instance, this doesn't. Here, of course, you might complain that I could have chosen the other angle, but this doesn't really matter because If you choose the other angle, the tangent changes by 1/. And when you take log, it changes by the sign. When you take absolute value, it's completely forgotten. Okay, so. The cross rate. Theta half, really? Yes, you're right. Yeah, you're right. Thank you. Right. I had said that the computation yesterday night, right? Thanks. Yeah, you're right. It's definitely a factor. Okay, so now we say that F is quasi-symmetric if this norm is, this supremum is finite. Okay, so basically and this effect again, similar to above, is that F is, so the normal cross ratio is equal to 0. Equal to 0 basically means that all symmetric quadruples are centrosymmetric quadruples, and this is equivalent to F being a transformation in PSL to R. Okay, so basically there is sort of an analogy. Here, the quasi-conformal maps are those that send circles to ellipses of bounded ellipticity, and this constant, where is it? Very lost. Yeah, this K here measures how far the map is from being conformal. Okay, among those that stretch circles to ellipses of bounded ellipticity, that constant measures how far the map is from being conformal. Here, being quasi-symmetric means that symmetric quadruples are sent to quadruples which are not symmetric, but for which this angle is bounded, okay? So, among all symmetric quadruples, the image have the property that the geodesics intersect with the bounded angle in the image. And this quantity measures how far the map is from being an element of PSL to R, okay? And there is a relation between the two, so this is a fact which is known in Teichmüller theory. So I say two ways. So if F, so now we look at maps from the disk to the disk. If F is quasi-conformal, then it extends to a quasi-symmetric map of the circle. Or let me say H2. Although this doesn't depend on the hyperbolic metric. This is purely a conformal notion, but a quasi-symmetric map, let's say small f from RP1 to RP1. And conversely, every quasi-symmetric F admits a quasi-conformal extension. Excellent. So now we go back to minimal Lagrangian maps. Yes. Okay. So it is from this point of view that I want to study how good minimal Lagrangian maps are. So here is the starting point, is the theorem. It's again Bonsanti-Schlenker. So for every quasi-symmetric mu is now phi, I mean, the minimal Lagrangian extension is quasi-conformal. Yesterday we have seen that there is a minimal Lagrangian extension, and that one is quasi-conformal. Of course, there can be extensions here which are not quasi-conformal. I mean, in general, F says that F admits some quasi-conformal extension. There are others which are not. The minimal Lagrangian map is quasi-conformal. Okay. And the proof is, again, through anti-de Sitter geometry. So let me remind you how the minimal Lagrangian, very quickly, minimal Lagrangian map is constructed. It's a composition of these two Gauss maps. Okay, and we had good formulas for basically the differential of these maps. So one can compute the dilatation of this map in terms of the geometry of the maximal surface, and the computation is that at a point at a point Z, which is let's say the image via the left Gauss map of point P, a point on the maximal surface that we have used to construct the extension, the dilatation at Z is equal to lambda of P 1 minus lambda of P to the square, where now lambda is the principal curvature. Yesterday I used kappa for them, but there's too many kappas and k's, so now we write where A is the shape operator. We diagonalize to lambda of P minus lambda of P because it's traceless, and say lambda is positive. Okay, so we have this formula. So in particular, the thing that we have to keep in mind from this formula is that, so the sup of the maximal dilatation is finite. But this quantity is finite if and only if we already know that lambda is always less than or equal to 1. We have said that yesterday. It was a maximum principle. And this quantity is finite if lambda doesn't approach 1. So if and only if the sup of lambda of P over all points in the maximal surface is strictly less than 1, and this is also equivalent to the sup of the curvature of sigma is strictly less than 0, because by the Gauss equation we had the curvature. Here I'm writing curvature because, as I said, there's too many k's. Curvature of sigma is minus 1 minus the determinant A, so this is minus 1 plus lambda squared. Okay. So these things are equivalent. This is really the way they prove this theorem. So they show that if the boundary is quasi-symmetric, then the curvature, that either this one or this one, they are equivalent. Okay. So the goal is to sort of understand further. So from this point of view, it's a good extension because when the boundary is quasi-symmetric, it does the best thing that it can do. It is quasi-conformal. I want to study sort of further how optimal it is. So here is a theorem. So let's start by some quantitative optimality. Okay, so here is the theorem. So there exists a constant greater than 0 such that under the usual assumptions, so for a quasi-symmetric, the same assumption, for a quasi-symmetric circular morphism, we consider the minimal Lagrangian extension phi, okay? So the logarithm of k phi is bounded by a constant times the cross-ratio norm. Okay. So it's really sort of a uniform, let's say less than or equal, because of course when, so this is a quantitative version of this one, right? That doesn't just say that one is finite if and only if the other is finite. It gives an inequality, and moreover, observe that, so when phi is an element of BSL2R, this thing is 0, so the maximal dilatation is 1. So in particular, this shows that the minimal Lagrangian extension of a Maybury transformation is an isometry, okay? And sort of quantifies actually how far they are. And the idea of the proof is really having quantitative estimates everywhere here. So sort of study not only saying that curvature stays away from 0, but studying how much it stays away from 0 in terms of the boundary data. And let me make some comparison with other extensions. So there are many other more classical extensions in extensions in tight Miller theory. So for instance, I won't define them, but there is the Berling-Alfors extension, and there is the Duo-Earle. And the same problem was studied for these extensions. So for the Berling-Alfors, we have that the logarithm of k is bounded, this is much more explicit, so it's bounded by twice norm of cross ratio, or also by norm of cross ratio plus the log of 2. For the Duo-Earle, it's less explicit constants. So this was proven by Berling-Alfors in 56, and this by Leto in 83. And then this was Duo-Earle themselves in 86. And then Hu and Musician. This was only, sorry, this is only for small cross-ratio norm. And then Hu and Musician 2012 have a result that holds all the time. So basically putting the two together, that the same holds. So when I started thinking about this problem, I discussed with Jean-Marc Schlenker, who, like me, likes a lot minimal Lagrangian extensions, and he told me we must beat Duo-Earle. And at the end, the constant, I'd like to have this constant more explicit. I didn't manage, so at the end, it's that we don't do better than Duo-Earle, but it was really, at some point, we really felt like a competition. Yeah. Yes, exactly. This is the, okay, this is the dilatation of the Berling-Alfors extension. These are other extensions. It's the same thing, that they construct other types of extensions. They give themselves a circular homomorphism. No, it's not minimal Lagrangian. No, this is some other extension. I will not define, sorry, I won't have time, but it was just sort of an overview of the problem. And other questions? Yeah. That's what I was about to say. So I actually sort of studied the sharpness of this result. I'll write here. So there is a lower bound for the minimal Lagrangian, which is the following. Is greater than basically 1/2, or you can basically do as close to 1/2 as you wish times this, but only for this norm of cross ratio small. Okay? So for small values, you can't do better. Actually, there is really inequality on the other side. Here the constant is explicit, and there are also examples. In certain cases, this can be computed. It's difficult in general to compute this math, but some example, this is explicit. So I have some families of example where basically the ratio log of k phi, let's say phi t over the cross ratio norm of phi t, so I have one parameter family, is equal to 2 over pi, which is 0.64. And this is for phi t goes to 0, okay? So this is the case where we are close to 0. So this bound is not very far from actually being, in some sense, then of course it depends how much you measure. And then I also have an example for large values. So here we have the cross ratio norm is going to infinity. And here I get a limit which is square root of 2 over 2, so it's 0.71. So I don't know, there might be hope that actually this constant is not so bad. Actually, it's not a billion, but I don't know how to prove it. Okay. Any question? Now I want to turn to some more qualitative optimality. So there's certain classes of quasi-symmetric, quasi-conform, quasi-symmetric homomorphisms that are sort of better than others, but from a more qualitative viewpoint. So not just in terms of how large these quantities are, but some other property. Where is my paper? It's here. So I won't define many things actually, but there is a class of circular homomorphisms which is called symmetric. It's symmetric. So this has some intrinsic definition, which is basically saying that so the cross ratio of f of q is actually going to -1 when a quadruple is diverging. But I don't want really to give the definition. But heuristically, when you have quadruples that sort of escape far away, the symmetric quadruples, they escape far away. When you look at their image, they tend to be symmetric also in the image. And so this is also sorry about the terminology, but the quadruple is called symmetric when intersection is orthogonal, and also the map is called symmetric when it has this property that, however, I don't define in detail. But there is a characterization. So it is symmetric if and only if it admits an extension which is not only quasi-conformal, has the property that the dilatation extension F, such that the dilatation goes to 0 as Z approaches the boundary, RP1 approaches the boundary of H2. And this is called asymptotically conformal. Sorry, to 1. Thank you. To 1. Yeah, 1 is the case, the conformal case. Okay. And theorem, which we might decide to write down someday, is that so F is symmetric if and only if the minimal Lagrangian extension is asymptotically conformal. So sort of, again, the minimal Lagrangian map does the best that you could hope when the boundary data has this property, this symmetric property. This is an optimality, from my point of view, this is what I call optimality of the extension, but it's not quantitative, it's really qualitative. How does the proof go? Very quickly, basically show that the curvature of the maximal surface, well, it goes to -1, towards the boundary of the maximal surface. So it approaches the value that you have in a totally geodesic case which corresponds to an isometric extension. And now there is another class. Again, this is the last thing I want to talk about. There's another class which is more intriguing for me, more mysterious. And this is the Weil-Peterson class. So F is a Weil-Peterson quasi-symmetric, say, implicit. Homomorphism. So there are many characterizations of this, but they are all quite complicated. Again, I won't give the definition. I won't even try to sketch the definition. But the characterization is that if and only if it admits an extension F such that now instead of requiring that the dilatation goes to 1, we have a sort of L2 type condition. So we don't require this only asymptotically conformal, but we require that it decays in a certain way. So such that the integral on H2 of small k of f, which are now defined, square, integrated with respect to the area form of H2, is finite. So what is small k? It's a quantity that you cook up out of big K, designed in such a way that it goes to 0 when big K goes to 1. Because as you remarked, there was a 1 there, not a 0, which is sometimes annoying. So this is Kf minus 1 over Kf plus 1. So actually, we could have taken the log here. But I mean, the behavior close to 0 is the same. But it's classically defined like that because basically this is the modulus. If you know what it is, this is the modulus of the Beltrami differential. So this condition is actually called L2 integrable Beltrami differential. Didn't hear, sorry. Yes, exactly, yes. Yeah, so this is what is that? It's del bar F over del F, the modulus. This is okay. So, and why are they intriguing? Well, here I'll be very vague, but it turns out that on the space of quasi-symmetric homomorphisms up to PSL2R, this is called the universal Tech-Miller space. It's a complicated object of infinite dimension. And by the work of Takhtajan and Theo, which now I need my notes to write. In 2006. So this space of quasi-symmetric homomorphism up to PSL2R has a structure of an infinite dimensional Kähler metric, which gives a very complicated topology, which is not even connected with respect to this topology. But these guys are a connected component and are the closure. So for the let's say Kähler structure, infinite dimensional Kähler structure, Weil-Peterson are the closure of smooth homomorphisms, of diffeomorphisms, sorry. So it's sort of natural to study also from this point of view. Okay. So of course the conjecture now would be, according to what I've said so far, is that F is Weil-Peterson, or let's say phi. I use F, small f, big F for general map, and big phi for the minimal Lagrangian extension. So phi is Weil-Peterson if and only if the minimal Lagrangian extension has L2 Beltrami, L2 integrable Beltrami. This is still a conjecture. We don't know how to prove it. Yeah, so it's very complicated, but this infinite dimensional Kähler structure gives a topology to universal Tech-Miller space, which is not the usual one. It's more complicated. And it turns out that the smooth homomorphisms are all in the same connected component, and their closure are precisely for this complicated topology. Their closure is precisely the space of Weil-Peterson homomorphisms, which, if you want to define intrinsically, it's complicated. It requires some work. Yeah. What did I write? Yeah. It's the closure of the diffeomorphisms of S1. Yes, this is purely on the boundary. But okay, we have a partial result. The result is that if phi is regular enough, so phi is from RP1 is C3 alpha, then the XT minimal Lagrangian extension does what you would expect to do, but only with this stronger assumption, because this is in particular Weil-Peterson, by the above discussion, has L2 integrable Beltrami. And of course, the proof uses anti-de Sitter geometry. So the way we prove it is as a consequence of the following result. And so this is now a statement for maximal surfaces. So if sigma, which is the maximal surface in ADS 3, has, so is such that its boundary, so lambda is C3 alpha, so if it has C3 alpha boundary, then what we have is that when we integrate over the maximal surface, we integrate the principal curvature. Well, I said lambda is the positive one, so I don't need to take the absolute value to the power of S with respect to the area form of sigma, or the area form of the first fundamental form of sigma. This is finite for all S at least 1. Okay? This actually holds for surfaces in more general in H2n, actually. But let's forget about it. It holds in a more general setting of pseudo-hyperbolic, maximal submanifolds in pseudo-hyperbolic spaces. In particular, the integral of the curvature, the square curvature, is finite. This is a condition that has been studied in other settings. It's called finite renormalized area. Okay. And I'll just conclude by saying, so from this theorem, how does this follow? This is an easy computation, but however, it's based on several things that we have seen. So it's a proof of this implication. How does it work? Well, we had a formula for the maximal dilatation of phi, which was 1 plus lambda over 1 minus lambda to the square. Then we need to compute also the small k phi. So this was by definition k phi minus 1 over k phi plus 1. So it is just, now one computes and one finds that small k as an expression in terms of lambda. So small k at the point z. Yeah, so this is the point z, and this is the point p. Z is a point in the disk, and p is a point on the surface. So this is equal to 2 lambda of p over 1 plus lambda squared of p, just a computation. The important thing is that this is a big O of lambda of p. Okay. I'll just finish here. So basically what we have to compare is the integral over H2 of this. This is the definition of L2 Beltrami. Okay. And we want to compare with the integral of lambda square with respect to the area of the first fundamental form, which we know it's finite by our theorem, our second theorem, second on the board, over sigma, okay? But, so this thing is bounded by this thing up to a constant, okay? What we need to do is to compare the area forms. But here we had a formula, because yesterday, with the formula for the area forms. So if we pull back we need to pull back by the left Gauss math, the star of the D area form of H2. This was 1 plus the determinant of A times the area form of first fundamental form. This is, so this is 1 minus lambda squared, so it's less than 1. So this is less than or equal to dAi. So this goes in a good direction. So basically, you have this is bounded by this up to a constant. And therefore, the second theorem immediately implies the first one. Of course, if we can prove, but this seems to be harder, the second theorem for Weil-Peterson boundary data, then we will have the conjecture which I have just erased. Okay, I'll stop here. Thank you very much.